Does it look okay? All right, so
It
let's
looks
start
fine
again.
to me as well.
So the NJAG May meeting every year is to celebrate students that we know that have done research projects during the last school year. And this year we are honored to have 3 schools representative. We have University of Scranton, NJIT in Newark, and Montclair State University here in Montclair. And the projects that have been featured this year, I think, are really all interesting, and they're all very different from each other. So I think we should start with Shaf Sarwar from University of Scranton, opportunities for research and education with a small radio telescope.
So do I just start?
Yes.
Okay.
Share your screen.
Screen. Okay, is that visible to everyone?
Yay.
Yes, I see.
Okay, perfect.
Looks
So,
great.
sorry, what?
You said it looks great.
Okay, thank you. All right, so hi everyone. My name is Shaf Sarwar. I am a student at the University of Scranton and currently a physics major. I might be declaring a second major, I don't know. I'm always confused. But currently I'm in my 3rd year and I have been working with Dr. Nathaniel Frizzell for a year and a half and helping him with different research projects. And at the university, we have a broken radio telescope that I've been trying to getting to work, and this poster is basically going to talk about that. And I will also be working over this summer on some other radio telescope related research, and I'll be talking about that as well. So basically, I'm just going to zoom into the poster because I think that's the easiest way for everyone to see it, I guess. And
Thank you.
Yeah, so basically I will start with what a radio telescope essentially is. It is basically a giant dish antenna which is in a way specialized to receive hydrogen signals that come from the universe, and hydrogen being the most abundant gas or element in the universe, about 75%, actually turns out to send radio signals, and the source of those signals is the hydrogen spin flip. Now, the hydrogen spin flip is a spin transition of the hydrogen atom, the electron of the hydrogen atom, which causes the energy level to change, and corresponding to that energy level, the hydrogen atom releases a photon, which is about 1420 megahertz in frequency. And it corresponds with the 21 centimeter line that we see for H1. So essentially, these radio telescopes are specialized to receive these signals from hydrogen. And because it is so abundant in the universe, we can see those signals coming in on Earth and passing through our atmosphere and everything. So as you can see here, we have a picture of a radio telescope. On the left side of the picture is the Loyola Science Center, which is one of the buildings at the University of Scranton. And this is where I take almost all of my classes. Being a physics major, this is like most of my where I spend my time. And on the right side is a dish antenna, which is about 3 meters in diameter. And this is on top of that Loyola Science Center. So as you can see, there's a few missing panels on this dish. So after the installation, apparently this dish was flipped due to like a strong gust of wind, and it incurred some damages on the wiring and everything. So last summer, I spent some time trying to collect some data off of it, but it was not very reliable in the sense, because we tried to see if we could see any known radio sources, but we really couldn't. So that's the radio telescope situation at the university right now. But because that doesn't stop me, I guess I asked Dr. Frizzell if he could get me in contact with someone who could give me some data, and he got me in contact with Dr. Rich Russell, who is a member of SARA, and he agreed to give me some data and play around with it. And so yeah, a little bit about the dish. It is about the receiver, actually. So we do have a SpectraCyber receiver at the university, which specializes at receiving 1420 megahertz signals. and it can detect those subtle shifts in frequencies. And well, it turns out those subtle shifts in frequencies are due to the Doppler shift, and I'll talk about that a little bit in my next section. So so basically, one of the projects that I really got interested in was being able to estimate the mass of the Milky Way using H1 measurements. And it does not sound very obvious, but apparently we can do that. And one of my goals over this summer is to try and replicate some of the existing results that I'll be asking Dr. Russell, and maybe hopefully if I can collect some data off of the dish at the university, trying to replicate results from that as well. So essentially, we point the dish using celestial coordinates, which consists of right ascension and declination. And these celestial coordinates are obtained by converting galactic coordinates, which consists of a latitude and a longitude. And because we're looking at the plane of the galaxy, one of these coordinates is, of course, at 0. And then we only vary the other one in 5-degree increments. And using software like different astronomy softwares, we can easily calculate those numbers and point the dish in the right direction. So this is one of the plots that I obtained from Dr. Russell, and it is a frequency versus signal strength plot. And you can see that it has a slight peak in the middle. And using that, we'll zoom into it a little bit more. And using that peak, essentially, we can determine what the frequency shift is of the incoming signal. And you can see there's a very slight offset from the 0 point at the x-axis from the peak of the frequency, from the peak of the signal. And that essentially is the Doppler shift that I was talking about earlier. And essentially what happens is that when the target object that we're looking at, when it is moving away from us or away from our observation point, the telescope, we see the frequency is slightly offset, and it is lowered from the 0 point. The x-axis on the frequency versus signal strength plot is offset by 1420 megahertz. So the 0 actually corresponds to the exact 1420 megahertz value in the middle. And so because in this particular plot it is lowered, we know that the object that we're looking at is moving away from us. And well, we can obtain a bunch of these plots and determine the particular velocity using different formulas for Doppler shift. And we can plot these velocities in one of these graphs, which is a radial velocity versus galactic latitude plot. So a little bit about this plot. So the gray portion of this plot is actually taken from the Harvard-Smithsonian Center for Astrophysics. And the good thing about this plot is that it labels these different galactic arms on it, along with the galactic longitudes. And the red dots are the velocity calculations overlaid on that plot. And you can see there's some kind of correspondence. And essentially, looking at this plot, we can, in some sense, say that yes, the data that we collected and the calculations we made are somewhat consistent with what we we already know. And we know that using these H1 measurements, we can figure out what the velocity of the Milky Way galaxy and its different arms is. And one of my goals over the summer, the upcoming summer, is to try and replicate these plots. And I will be collecting data from Dr. Russell that he has collected over the past few months and in the last year in particular. Other than that, these particular radio telescopes might also be useful in observing fast radio bursts. I do not know much about them because apparently much of the radio astronomy community doesn't know about them either. So this is something that I will probably look into and see if I can make any detections or not. Apart from that, we might have some electrical engineers work on a designable, swappable feed for our antenna upstairs. And well, this is something that we could probably incorporate in one of the future projects. And Yeah, that's pretty much it. I want to acknowledge Dr. Frizzell for helping me and Dr. Russell for helping me create this poster, and also Dr. Mary Lewis from Montclair State with her tips and suggestions. And these are my references.
Thank you very much. Are there any questions for Shaf?
Yes, I have a question, Mary Lou.
Yeah.
Thank you, Shaf. Very nice presentation.
Thank you.
I just was curious. Can you give me an example of some of the specific objects that you are looking at or pointing the radio telescope at?
I believe it is one of the galactic arms. I'm not sure what the exact one is. It might be Cygnus. I'm not 100% certain.
Okay.
Yes.
And how long have you been doing this this study?
So this data is I have received from Dr. Russell. I haven't conducted this study myself. I will be asking for more data that I can manipulate myself over the summer. So I have to reproduce these plots.
Okay, thank you.
Yes.
So the idea would be if you had a radio telescope that was actually working, it didn't have panels missing like this poor thing.
Yeah.
You could point it at different parts of the sky. So track longitude every 5 degrees. So that's 70 some pointings around the sky, and take an observation for, and we don't know how long, perhaps a half an hour, perhaps a whole hour, perhaps 2 hours, to get a figure like the one that's in the middle of the poster with the peak in it.
Yeah.
And then after you accumulate a whole bunch of these, so all 72 around the sky if possible, then you put them on a graph like the one in the upper right.
That's
where
right.
you have the longitude going along and then the Doppler shift that you have read off these pointy graphs. And from that, you can measure the velocity curve. So the Doppler shift becomes a velocity, and then that goes into a Keplerian sort of calculation, and then you get the mass of the Milky Way.
That's right.
So it takes quite a bit of observation to actually be able to do that.
Exactly.
And
So
at the moment he has one observation, and it was done by Dr. Russell, not him. So.
Yes.
Okay.
So essentially the whole idea was because we did not have a working radio telescope, and I went to Dr. Frizzell asking, what should I do? He said that this should not stop you from actually doing something. And so I actually wrote a proposal asking the university to pay me over the summer for research. And so I would be getting data from Dr. Russell and reproducing these results. But again, we do not have a working radio telescope that can collect the data itself. So, but again, I want to learn how to do this, and I think this would be a good opportunity to do that.
Very good. Good luck.
Thank you.
And so Chris, the things that you're looking at are individual clouds of gas, hydrogen gas, in the various spiral arms in the Milky Way.
Okay.
And so in some directions, you can look through one spiral arm to see the next one. So you get 2 peaks. And other places you can just see the nearest spiral arm, and that's all, and you get only a single peak. So there's a lot of deciphering of the data once you get these various pointings throughout the sky. And luckily, radio waves do not have to be done just at night. You could do it during the day as well. So that's better than optical astronomy in that sense.
Yeah.
So they're individual clouds which are lined up in this spiral fashion around the center of the Milky Way.
Okay. Good. Thank you.
So I have a question. Are there any plans to repair the telescope? And if so, how do you plan to filter out the background noise from the rest of Scranton, the airport, the other buildings, and whatnot?
Yeah, so Dr. Frizzell recently was applying for a ARDC grant for getting some ham radio antennas up there, and we tried asking them money for sponsoring one of the radio telescope replacements, and they refused. So we're still looking for finding money for this replacement. I don't think it would be possible in my time that I'll be at Scranton, but as far as like the noise pollution or like the interference is concerned, I think we should have some. I think there should be some built-in filters in the receiver that can do that. But again, I'm not 100% certain on that. Dr. Spalletta is also one of our physics professors, and he initially had this installed and bought the equipment. So I believe he had something in here that would filter out the noise.
But that's a real problem. Cities have light pollution at all frequencies, and that makes it difficult. So we know the frequency of neutral hydrogen at 1420 megahertz, and one gets a filter, a notch filter, which just looks at that frequency plus a little bit on each side, and that takes most of the pollution away. It's called radio frequency interference problem. Yeah. Any other questions? Okay, then we could, I think, move on. Thank you, Shaf. That was very good.
Thank you so much.
To the next presentation is by Diego Sanchez from NJIT, climatology of large-scale traveling on ionospheric disturbances observed by ham-sci amateur radio with connections to geospace and neutral atmospheric sources. Okay, go Diego.
So, can everyone see my screen?
Yes.
Yes.
Awesome. Yep. Thank you, Mary Lou. Yes. So my name is Diego Sanchez. And so just to start off, space weather is the branch of space physics concerned with the time variations within the solar system, specifically around Earth. And hold on one second. Zoom is blocking my view. These generally include things like solar flares, geomagnetic storms, the aurora, and a few others. And these can have catastrophic effects on spacecraft and satellites. We actually had a few months ago in February, SpaceX had launched a new batch of Starlink satellites, 49 of them. And a geomagnetic storm came out of nowhere and knocked 40 of them out. They all burned up in the atmosphere. That was over $50 million, I think, lost. And there's currently little to no forecasting capabilities for these kinds of events. So one of these types of events are what we call traveling ionospheric disturbances. These are quasi-periodic variations of F-region electron density. They affect radio wave propagation. Large-scale TIDs, which is the main focus of the study, they have wavelengths typically over 1,000 kilometers, periodicities from between 30 to 180 minutes. They're often influenced by auroral electric enhancement and particle precipitation. The current instruments that we have to observe these events, primarily super Darn radars, GPS, total electron content plots, and ionosons. But all of these have very low coverage. So this is an example of what happens to radio, HF radio propagation when a TID goes through the ionosphere. As the ionosphere becomes perturbed, the actual amount of refraction changes, which changes the total distance that the refracted radio wave actually travels. And the main data sources for this study were, there are two passive ham radio data sets that we used. One is the reverse beacon network, and the other one is the weak signal propagation reporting network. These are passive networks that just record ham radio usage that they pick up over 24-hour periods. Then we also have, as mentioned earlier, super Darn radars, GPS TC plots, and ionosons. So this is a visualization of those two ham radio data sets that we have. So here we have A and B up on the top. These are for the geomagnetic storm indices and solar flare activity through the GO satellites. These are mainly to discard any disturbances that we see in the ham radio data that might be caused by other things besides TIDs. We have on the bottom left the geolocation of all the spots. What's shown there down here on the left, those are the midpoints between transmitters and receivers that are recorded within WhisperNet and RBN. And here, these are the actual the histograms that we have that show the actual ham radio data. So on our y-axis, this is the distance between transmitter and receiver. We have currently from 500 to 2,500 kilometers, and this is over a 24-hour period. And this red line here is showing exactly what we're looking for. So as the usually you'd see a straight line in the minimum skip distance. So the minimum distance that we have that the ionosphere is allowing for that radio propagation usually be closer to a flat line going straight across here. Whenever we have a TID going through the ionosphere, you actually see that the minimum distance, these kind of wave structures start to appear within these histograms. So these are indications that there may be a TID going through the ionosphere for this particular time. So first, to kind of the main focus of this is trying to develop a new method of tracking traveling ionospheric disturbances, add another tool. So the first thing that we did was compare days that we found TID structures in the ham radio data to other instruments. So this is an example of TIDs as observed by the Blackstone SuperDARN. So you can see here, SuperDARN radars perceive TIDs very similar to ham radio. You actually see these wave structures pop up in the short range distance for the radars. So for this day, the 3rd of November, we see the exact same or very similar wave structure, the exact same time of day as the ham radio data. The next we compared to was the GPS TEC total electron content. So for GPS TEC, radio range is shortest when total electron content is higher, or in these plots is shown as more red colors. So the higher the electron densities, more refraction we have, the communication range decreases. So just to kind of show, we have here from 18 UT to 21 UT, where we should see higher total electron content go across this time period. So I have here a movie from 18 UT to 21 UT for the GPS plots, and you should be able, if it plays, sorry. It's not playing for anyone, correct?
So try again, but do not play the movie.
Okay. 1 second, let me pull up. There we go. Can everyone see my screen?
Yes.
Yes.
Awesome. I hope that does not happen again. So I guess instead of risking that again, I'll just kind of explain what happens. So you see down here on the bottom of the GPS plot here, these are primarily all blue colors. This is indicative of lower total electron content, which coincides with the very beginning of the plot here. We have higher minimum distance here. As the time goes through on this movie that I have, you actually see a wave. So higher total electron content, more red colors kind of propagate southward in a wave kind of structure, which coincides very well with what we're kind of seeing in the ham radio plot on this left-hand side. So lastly, we compared it to ionoson data. So for these, there's two main geographic locations that we have the majority of ham radio spot data, which is primarily over Europe and the continental United States. So we found the closest ionosons to kind of where the center of our, where the spots are concentrated. So for Europe, we chose the Julius-Rue ionoson in Rügen, Germany. I apologize for that pronunciation. And for the US, we chose the Boulder ionoson in Colorado. So here, ionosons, how they work is they do a frequency sweep straight upwards towards the ionosphere, and whichever the highest frequency that is bounced back is what we call the FOF2. So the higher the frequency, the shortest the radio range is going to be. So there's going to be more refraction at higher electron densities. So we have here, wherever we see high peaks or higher frequencies being bounced back from the ionosphere is what we would expect to coincide with lower propagation distances for the ham radio spot data, which is exactly what we see here when we compared this year for January 26 for 2017. So this is for US. We have at the exact same times our low peaks for skip distance or propagation distance coincides with high values in FOF2. So once we went through, we found that pretty much for any day that we had, we could see TID structures in the ham radio data coincided with the other instruments. I went ahead and did a climatology using this new method. So first, just to kind of eliminate any inconsistencies in overall ham radio usage over the year, if any patterns that we found might have been associated with changes in ham radio usage as a whole, I went and found the average number of spots per month. And there doesn't seem to be any significant overall change or any kind of seasonal pattern in ham radio usage. And just to make sure that this couldn't be the cause of any findings or any results that we had later. And this is my first climatology for Europe. So what I did was for the entire year of 2017, I went through and I plotted daily visualizations of the ham radio data and just manually searched for any TID structures. And every time I found the structure, I would find the beginning and the end of the structure in the histogram and just add up the number of hours that the TID was, I was able to visually observe them in the histogram. And my initial findings were that there was much more activity during the winter months as opposed to the summer months, with a spike here in June that we don't quite know what's causing that spike. But we found similar results for the US as well, much more activity during the winter months as opposed to the summer months. This is very consistent with previous papers. So I did a direct comparison with a 2014 paper by Dr. Nathaniel Purcell, where he did a climatology of MSTIDs, medium scale traveling ionospheric disturbances, using super Darn radars. And they're very similar patterns. There was much more pronounced activity during the winter months as opposed to the summer months. What's interesting is super Darn, which is one of the main methods that we use for tracking TIDs, has very little to no summertime observation. Super Darn radars depend on ground scatter, and there's a pretty severe lack of ground scatter in the summertime, which means that down here on the bottom left, we have for quiet events, which are days, hours that have no noticeable disturbances in them. You would expect to see the exact opposite from any studies in actual TIDs. So if we're seeing more TID structures during the winter months, we expect to see more quiet events during the summer months. That is not a problem that the ham radio data has. So we actually have, when we looked for quiet events for the US, we could actually see that there is a significant increase in quiet events during the summertime, which is a pretty substantial advantage over super darn radars. And last, we started looking into potential drivers, what are causing these TID structures. So one first looked into auroral sources. And for that, we used the Kyoto Max AE index. And again, compared results to Nathaniel's 2014 paper using looking for MSTIDs with super darn data. And in both cases, there was enhanced max AE values for TID events. So whenever we had a TID event, it usually coincided with higher values of max AE, as opposed to quiet events that kind of geared towards closer to zero max AE values. So conclusions, TID activity was much more prominent during the late fall, ending in early spring. Ham radio data seems to be, we can actually observe TIDs using it. There's consistency with super darn GPS Ionoson observations. We have a much larger coverage over super darn and the Ionosons, especially over the summer months compared to super darn. We are, however, currently limited to only observing LSTIDs just because of the nature of the size of the locations that we have overall. We can only pick up things with very large wavelengths. But the ham radio overall traffic was not noticeably influenced by season. We don't know the exact mechanism quite yet. We're still looking into other sources, but initial results do show enhanced max AE values for times with TID events in them. And we are also currently trying to develop an automated detection system using machine learning image classification techniques. We have a very large swath of data going back more than 20 years. And we want to try to develop an automated system to be able to go through so much data. Thank you. Hope everyone enjoyed.
Thank you very much. That was very interesting. Do we have any questions about the
No
ionosphere?
question, but again, it's a great presentation. Thank you.
Thank you.
Okay.
Yeah, I've got a question. So I was thinking about this seasonal dependence. Naively, I might expect to see more disturbances in the summer, right? Because you're getting more insolation. So if there is a solar cause to it, you'd expect that the warmer months would be where you'd see that. Or is my intuition just totally off on this?
I'm actually not sure. I know that it's when it comes to radio propagation, summer months, there is you generally have generally higher TEC values. So it's going to be less observation capabilities, even with ham radio data, even though it does have more observation capabilities over things like super darn and the Ionosons, just because the ionosphere absorbs way more of the radio frequencies.
So you're saying that
I'm actually not sure.
They might
Yes.
still be there, you're just not seeing them.
Correct. They might still be there. Yes.
Okay. Any other questions?
So it would be
Okay.
interesting if there's a correlation with solar activity with the 11-year cycle.
Mhm.
And that's one of the things that the group is doing next, since we have more than 12 years of data now, is
Right.
to look for that.
Yep.
Very
But
good,
it
very
was-
nice presentation.
Thank you.
But it would seem that because the summer months, which are hotter, haven't got the sort of TIDs that one might expect, that possibly actual temperature has nothing much to do with it. One of the things we'd like to do also is to do this for the Southern Hemisphere, where summer and winter are reversed.
Yeah, and Mary Lou, is there any data from the Southern Hemisphere?
It's a much smaller amount. There are fewer ham operators in the Southern Hemisphere.
Mhm.
Yeah, much
Partly
fewer.
because there's a lot less land area. There are a few super darn radars down there, but very few. So there's a lot less data in general in the Southern Hemisphere, but there's some. And so one of the problems with this sort of phenomenon, these waves in the ionosphere, they're not a static thing, they're a wave. And so you're looking for not something, but something's derivative. And it's not clear at all what is it that sets these things going. People are looking for it.
Okay.
Thank you, Diego. Good job.
Thank you.
Yeah, very good.
Now perhaps we could move on to Michael.
Sorry. I apologize again.
So that's fine. So now we're going to have Michael Camillo from Montclair State. Inference on neutron star matter using mock NICER data. A lot of things to explain to us what all that means, Michael. Go.
Yeah, I'll try to share my screen now. Let's see. Do you see these slides?
Yes.
Yes.
Cool. Okay. So my work. First of all, hello. Nice to see you guys. My name is Michael Camillo. I'm a person who does research. A student does research at Montclair State. I have a concentration in astronomy, and my research this semester involved the study of neutron star matter using NICER data. And before we talk about specifics on how we manipulated that data, we'll have to begin with some necessary background to really appreciate the work. And I should also mention that I did this work under Dr. Sean Ghosh, who I think also did a presentation for this group a while back. So you might see some similar stuff there too. Okay, so for starters, we should talk about neutron stars. As some of you may know, they are the remnants of supermassive stars at least 10 times more massive than our sun. And when fusion in these supermassive stars ceases, when they're at their death, they have the potential to have protons and electrons in their core get squished together by gravity to form an amalgamation of solely neutrons. This amalgamation, what's left over, is the neutron star. And it's a luminous object. It is a star, just a very odd star at that. They are extremely dense, and because of their density, they fall into a category of star whose matter is completely unknown to us. There's no way of doing experiments in a lab here on Earth that could mimic that interior environment. They're really odd objects. Here we've got just some illustrations of neutron stars. I mean, there's not like a visible image of them in the visible spectrum or anything. This one here is actually pretty cool. It shows, there is a lot of mystery about the interior of a neutron star, and we'll talk about that soon too. And a very common phrase, which you might have heard of from my advisor too, it's very common in the field, is that a teaspoon of neutron star matter weighs more than a mountain. These kind of facts just make them very extreme objects. You hear the word extreme very often when reading about them. Okay, so in addition, neutron stars inherit the magnetic fields of their progenitor stars, their supermassive progenitor stars, the stars that they originally were. These magnetic fields can actually tangle up and get into knots, and eventually can rise up to the crust, heating that crust, and by heating it, X-rays are actually emitted. And these X-rays, once they reach Earth, can't exactly penetrate our atmosphere. So terrestrial telescopes are out of the question. They can't observe these X-ray pulses. So that requires a space telescope to do the job. And this is where a NICER comes in. NICER, or the Neutron Star Interior Composition Explorer. This instrument, which is a pretty interesting instrument, if you see these hexagons there, each of those is a X-ray telescope. So it's got multiple arrays of telescopes. I think it's a 7x8 grid. And this instrument, which is installed on the ISS, I think it was installed in 2017 of June, is capable of measuring these X-rays from neutron stars. And it measures them in pulses. And the reason for this pulse behavior is that hotspots on neutron stars come in and out of view from the perspective of the instrument. So as they come in and out of view, we kind of see that pulse in X-ray emission. And I guess, yeah, I have a decent illustration from some video there showing that, you can have an example here, you have 2 hotspots there. So you would imagine that when you observe these emissions, you get 2 little peaks in that raw, nicer data. Okay, so from these X-ray burst readings, the estimates can be made on the neutron stars mass and radius values. But when we make these, or when these estimates are made, there is uncertainty. So it's estimated as a distribution of values, essentially multiple values between the minimum and maximum value for mass and radius of a neutron star. So those are the constraints in place. And I guess we can move closer to the aim of this topic. So what we're interested in is the state of neutron star matter, the matter itself. And this is commonly referred to as the equation of state of neutron star matter. Now, this equation of state, which we kind of refer to as an EOS in these slides, it determines the pressure and density relation of neutron star matter. And in turn, from this relation of the pressure and density of neutron star matter, you can also get the relation between mass and radius. So these plots, which I made from just an equation of state that was proposed in the literature at some point, I was able to make a quick curve showing what this equation of state, what this model says is the relation between an increasing pressure, which is in the y, and the how it as you increase that pressure, the density of that matter increases, and that makes sense when you look at this other plot here. So as you increase mass of a neutron star, let's say it's accreting matter, now you have more gravity. So now the matter is under more pressure, and now it becomes even more dense, so it becomes more compact. And as you look at this curve here, you actually see that as you increase mass on the x, you will get a decrease in the radius of the neutron star. That's what this model, this particular model shows. Of course, we don't know if this is the true equation of state. There's many proposed models, and that's the underlying goal of the work is to make a really good estimate on the true equation of state of neutron stars, or of neutron star matter. Okay, so we can move on even closer to the work. Here's a kind of flow, which is we should keep in the background. Kind of the overarching data that's involved in this project. Here, you can see, you start off, NICER observes a particular neutron star, measures X-rays and gets pulses. And then from those pulses, a mass radius distribution can be estimated. That's just something done, that's been done in the literature before. Though that estimation from raw data to a mass radius distribution, which is shown here, isn't what my project entails. We left that because that's an entirely other project in its own right. That's a whole process. What our work was interested in was going from a mass radius distribution, going from a mass radius distribution, which you can see here, to going to a pressure density distribution. So this arrow here, I guess, shows, doesn't really show, but it kind of indicates all the work we did. I mean, we used a series of techniques, but yeah, that transition is what we're interested in. And it does often feel a little weird. The idea that you can, from a macro scale value or unit, like the mass and radius of a neutron star, of a star, the fact that you can extrapolate the relation of its matter at such a micro scale, the pressure and density relation is pretty weird to think about sometimes, but it is possible. I believe the main reason is that neutron stars are very simple objects. They are mainly made up of subatomic particles aside from their crust. So there is a very direct connection there. And I guess we saw that here. You can really tell how the mass radius curve is going to look depending on how this relation looks. Okay, so before we made this pipeline, I should say, we did develop a pipeline here, a series of functions that I wrote with the help of Dr. Ghosh in Python. I was able to make that transition from a mass radius distribution to a pressure density distribution. But we wanted to test out if this pipeline worked. I mean, we can't just make something and then, hope it works and then plug in data and get results and publish that. And we have to have a control group of some sort. So in this example here, what we did was, I keep these 3 images here just to show what the normal way of the normal transitions are. What we did was we in a sense, I guess the phrase would be, we kind of play God. We state that one of the proposed equations of state, which this one is called APR4, one that was published in the literature at some point. We take that relation, that model, and we say that this is the actual equation of state of neutron stars. So we want to simulate incoming data. We don't want to use real nicer data just yet because we are testing things. So we produced, like before, a mass radius curve from that model. And from there, we were able to kind of simulate a bad estimation of a bad estimation of the mass radius values by kind of spreading out that distribution, by adding deviation in it. So we are, in a sense, as the title of the work suggests, we are using mock data. And here it is. And actually, you can kind of see here, this is actually real, nicer produced data. So you can see that we didn't really make it look that close. We didn't realize that till later, but for our purposes of testing things out, it served this purpose. We were trying to, in the same way that you would estimate this distribution from real data, we were trying to just skip that part and see if we could make some mock data. And we did just that. And then from this mock data, we used a series of techniques, of data analysis techniques that I don't think we have time to talk about. And I don't know if it really helps get to the point of the work. But using a series of techniques, we were able to then get that pressure density distribution. And what we can then do is, like before in this previous slide, you can see that we were able to get a pressure density curve from a model. So we get this estimate of that pressure density relationship. As you can see, it's like a span of values in the horizontal direction, that span of blue. And we plotted over it the actual model, the actual pressure density curve from the model. And what this plot here proves is that our pipeline works. We were able to get a really messy mass radius distribution, and using our series of techniques, our pipeline that we developed this semester, we were able to then get an estimate of that pressure density relation with a very large set of values. I mean, this is a very large span. If you notice, the x-axis is it's changing by magnitudes. So that's a very large confidence interval. But it did properly estimate the pressure density relation, because you can see that that curve, that true curve for the model, is in that estimation, is in that span. So we know the pipeline works. We know for a fact that it can properly estimate the pressure density relationship. And I don't know if I stated it, but by understanding the pressure density relation of neutron star matter, we know the equation of state. And if we know the equation of state, there's other products that can come from that. So we know the pipeline works. From here, we went on to actually use real NICER data, which is very cool. We used data from a publication that was on the estimation of this distribution, which, like I said, it's a whole other project. They did all the work and got this estimate of mass radius values. So what we did is we took that data and we ran it on the pipeline, took a couple hours, and we got a pressure density relation estimate. Now, of course, you see that we don't have that red line like before. And that red line would be the true equation of state of neutron stars, but we don't know it. So that's kind of the mystery that's ongoing in the field. And I should say that if you get a very tight concentration of points, in a sense, if you get a really good estimate of those mass radius values, you would actually find that this span of values would get really tight, and you could sort of then extrapolate what that curve actually looks like. I mean, right now you can't really tell. It could be any number of infinite curves in this span. But somewhere in that span is the true equation of state of neutron stars. And hopefully we can develop this work more to actually, in some sense, estimate it. In addition, in the bottom here, you can see that we also did some work proving past proposed equations of state. So these are just some names of some models that were used, that were proposed for the EOS of neutron stars, APR4, SLI, H4, and whatnot. And we plotted this over this estimate from real data. And we can see that all these, all these equations of state are in line with our estimates. But from this little study we did, we can see that we have the potential to disprove models that can be proposed both in the past, that were proposed in the past, and that can be proposed in the future. So if somebody proposes a model, we can just plot it over, or rather we can fit it to, we can compare it to our estimate, or in a sense, visually just plot it over our data and see if it's in line, if it's in that estimate of density values. And yeah, I mean, that's as far as we got in the work at this point in the semester. I mean, we've only worked on it for a couple months, I think 3 months. So yeah, I guess
Thank
I
you,
should
Michael, that's really interesting. Neutron stars are such strange and wonderful objects in the sky, aren't they?
Yeah, and I should also state that there are some cool applications here. I mean, aside from just neutron stars being very cool and learning about their interior, you can also learn about a fundamental force, the strong nuclear force, by studying these objects. So that's one of the other reasons we do this work in the first place. I should quickly thank my advisor, Dr. Ghosh, for helping me throughout the work. And especially for the North Jersey Astronomy Club for listening about this whole thing, because I really don't talk about this work. There's not really many people to talk about it with. And of course, I should thank the people that funded the project, which is the New Jersey Space Consortium. So thanks for listening, guys.
Thank you very much. That was very
Very
interesting. Any questions?
Yes. This is Jeff. I have a question. Is there a theoretical limit to how dense the neutron star can get?
That's a good question. I mean, different models have different caps. One of the things about all those different models is I guess the qualitative wording for it is some models state that a neutron star is more squishy. In other words, as you increase pressure, density increases, so it gets smaller and smaller. So I guess those proposed models state that you can have a really high density. Others state that there's a cap, and those are called, I guess, what's the opposite of squishy? More solid models.
Rigid.
Yeah, rigid. Yeah, more rigid models. So different models say different things. I'm not sure if there's a theoretical true answer to that, but I guess that's still up in the air, would be my answer.
Okay.
Thank you.
Any other questions?
I have a question. How do you know that the star inherited from the mother star? You said that they inherit the magnetic fields of the supermassive star, their mom star.
Yeah.
How do you know that?
Right.
Star is the mom, and which are the baby neurons.
Right. Yeah, so I don't know if I know the exact manner in which they found that out. It may even just be a theoretical understanding of how neutron stars have magnetic fields in the first place and whatnot. It's a good question. I don't know if I know.
That is
I'm a total beginner, so
Yeah,
I'm a
nonetheless,
social worker. I picked up on like the mom baby star thing. So
that's great. That's a really, really good question. And it's not known for sure yet, but there are some examples of neutron stars for which the magnetic field can be measured pretty well. So you know what the baby has. And for some of those, you know what the precursor was, what the mom was. And you can compare those two in a few cases, and it's pretty much the same. But there could be other cases in which when the neutron star is formed, that some of the magnetic field gets ejected. And that would be really interesting. And we have not got cases like that, but people are looking for cases like that. So that's a very good question, and not totally for sure. So good question there. So I have a question. Some neutron stars are pulsars and they spin around.
Yeah.
Do you know, Michael, about the spin of the ones that give off the X-rays compared to the ones that just give off radio waves? Are they similar, or is it a different kind of subset?
Yeah, right. So pulsars, their beams are emitting radio waves, and so yeah, those radio waves I believe can be observed on Earth. And what the work here was on hotspots that emit X-rays. I wonder if their spins are different. I mean, I've seen some videos from NASA that show neutron stars spinning pretty slowly. That's a good
So that's
question.
something you could look into. Do you have any idea? So how long has the NICER equipment been working?
Since 2017, for sure. They installed it in June of 2017, and research on its data is still active. I mean, this mass radius distribution that we used here, that was published in 2019, 2 years later, close to 3. So I think it's still operational. I think they were going to stop its use, but then they renewed it. But I might be wrong. I might be getting confused with another mission. But it is still in use, and it's. Do
you have any idea during this time, so 4 or 5 years, how many sets of pulses they got, like your first picture there?
Yeah. So when I originally, before we stated that we weren't going to do that mass radius estimation, I wanted to try it out. So I actually went into the database where they have all that raw data from NICER. And it's cool. They have data from each of those 56 specific telescopes. And the database was full. So I think they measured a lot of neutron stars. I saw at least 100. Like, there were many observations, so there's a lot of potential. There's a lot of data for sure.
Well, that's great. That'll keep you busy next year, and you could come back and tell us how much you've really learned from all those.
Yeah, this is from one neutron star, so yeah, there's a lot of potential.
Okay, cool. Well, thank you very much. So
Yeah,
now we're going to move on. Oh, another question. Sorry.
Yeah, I have a quick question. Are they measuring temperature as well? I mean, I know nothing about neutron stars, so I'm kind of curious as to, what some of the dynamics are.
Well, the raw data is just what they're really measuring is the time when they receive those X-rays and the intensity. How many of those photons those telescopes take in. So that's the raw data side. I don't know if I've ever seen anything on the temperature of neutron stars. I think the main focus usually is mass radius, pressure density. Temperature. Yeah, I don't really see much on temperature. So I don't think that's one of the things they look to.
Okay. Any other questions? Well,
Yes,
thank you very much, Michael. That's really neat. Another question?
Yeah, Mary Liz, Jeff again. I think I was reading that neutron stars are about the size of Manhattan.
Yes.
Oh, I forgot the best part. Yeah, I should have said that. Yeah, neutron. So I did say neutron stars are compact. I should have included that. Yeah, they are very small. They are super small. They're at least 1.4 solar masses. They can be up to maybe 3 solar masses. So they're massive, but they're very small, right? Like just like the size of a city. So yeah, they're very extreme objects. That's another reason why they're so extreme. Yeah.
Yeah, fascinating too.
Very
Yeah.
fascinating. Yeah. Cool. Okay, so now we can move on to Kevin Johannmeyer, Montclair State, sonification of gravitational wave data, creating a web-based application. This sounds so cool.
Hi, everyone. My name is Kevin Johannmeyer. I was a physics major as an undergraduate at Montclair State. I graduated in 2016, so I actually just returned to school and I did my master's in applied math. And I actually just finished my master's a couple hours ago. I had my last presentation.
Hey, congratulations.
Thank you. So this was my capstone project. So while I was an applied math major, I still worked with Dr. Favada in the physics department, who's the chairperson. And as Dr. West said before, my project's called Sonification of Gravitational Wave Data, creating a web-based application. So some of Dr. Favada's research involves sonifying gravitational waves. So I'm going to talk about what gravitational waves are. And here are some examples of the applications I made, and I'll explain these coming up in a bit. And basically what he does is he sonifies them. So you have some kind of signal like this, and you could analyze the data. You could look at the graph visually. And while these events don't necessarily make these sounds, it's another means of interpreting the data by just listening to the sound of the waveform. And so he typically does this in Maple, and that's the programming language of his choice. So anytime somebody like reaches out to him and says, hey, I want a gravitational wave sound for this specific event, he has to go in and he has to reprogram it manually. So one of our goals was to kind of like automate this and make like a very user-friendly like graphical interface that anyone could use, and it could be hosted online. So we decided to do this through JavaScript. And also I'm a high school physics teacher. I teach at Passaic County Technical Institute. And I wanted to lower the barrier of entry to study gravitational waves. So after teaching physics for a few years, I always have students that are like, I want to study black holes. I want to study neutron stars like Michael was talking about, all these things, but at the same time, don't really know the fundamentals of physics and are just like entering into physics. So to study this stuff properly, you need like several semesters of calculus and higher level physics and that kind of stuff. So this is something that can make it accessible to high school students that don't necessarily have that math background. And it's a little bit less formal than picking up like a general relativity textbook or something like that. So what are gravitational waves and how are they detected? So basically gravitational waves are disturbances in space-time caused by accelerating masses. So if you take your arms and you move them around like this, you are theoretically generating gravitational waves, these ripples in space-time, but they're going to be too weak that you wouldn't be able to detect them. So the types of events that we look for with gravitational waves are some of the things Michael was talking about, like neutron stars. So we're really looking for the collision and merger of neutron stars and black holes. Since they're so massive and they have such a short orbital period and everything like that, it deforms space-time in a more detectable manner. So if you take a look at this left diagram here, this is like a Michelson interferometer. And we basically have a laser that is going, and it goes through this beam splitter, and then it goes down these two arms. So it goes like up the screen and to the right. Then they bounce off the mirror, and then they recombine at the beam splitter. And then the light actually like is focused onto this detector here. So when the length of the two arms are equal, then the signals and of the lasers are perfectly out of phase. So there's actually like total destructive interference, and then there's nothing on the detector. But as those mirrors adjust and they move in length, then that's when you get a signal on the detector. So basically, when a gravitational wave hits the Earth, those mirrors are shifted by a very small amount because the space-time continuum is being altered and rippled essentially. So the way we do this, we basically take this simple Michelson Interferometer and we blow it up to a bigger scale. So over here, I think this is the LIGO detector in Louisiana, if I remember right. There's one in Louisiana and there's one in Washington. And each of these arms is 4 kilometers. And then also the light goes back and forth in the arms about 300 times just to make the length longer. So the change in distance that we're looking at is extremely small. It's on the order of like 1,000th the diameter of a proton. So this animation here is drastically exaggerated just to get the point across and that kind of stuff. So we're looking at really small changes over this like 4 kilometer distance or 1,200 kilometer if you consider that it goes back and forth 300 times. All right, so this is I didn't make this plot, I got this off YouTube, but basically these are, this is a binary black hole system, so they're orbiting each other. And if you look, this is actually the gravitational wave strain. This is actually one component of it. There's 2 polarizations. And this is what we're plotting on my application. And what this represents is the ratio of the change. So like I said, it's like a very small change in length divided by like the total length. So we're dividing a really small number divided by a larger number in the denominator. So you'll see that on this plot here, they have like times 10 to the negative 20th. So a lot of these signals are very, very weak. And we have to make sure that the noise, we filter out noise properly because any amount of noise basically is going to overshadow the signal. So here's some of the mathematics in it. So I don't know if this is the right audience to really go through this thoroughly, but like I said, my capstone was in applied math and I'm using the same presentation I had to do a week ago. So I could go through this quicker if nobody cares the details. But basically h of t is the strain. So that's what we're plotting. It's a function of time. And then we have like a, which is like this amplitude here. And then we have a velocity function. So that's the velocity of the orbiting objects. And then also we have phi, which is the orbital phase. So the way we get these expressions for v of t and phi of t is we have to solve these differential equations here. And then so we have analytic solutions for them. So if we wanted a full analytic solution of h of t, I could actually take this expression and I could plug it into v and v over here. And then I could also do that with the phi. So I could take this and I could plug it in here and here. So then we would have one massive analytic equation to plot the strain. But I actually solved this numerically because I did it through JavaScript and on the computer. So I actually just evaluated them separate at each discrete time step. So I evaluated VT at like one time step, VT at one time step, and then I would take those values and plug them in to these to find the strain at that particular time. And then it's a loop, so it just continues to do that for the whole domain. Alpha here is a dummy constant essentially, and we could choose that to be anywhere between 0 and 1, and we'll look at that behavior coming up. So if you notice, if this is 0, this actually like higher order term all goes to 0. It's just multiplying by 0, and this extra term represents like a higher order harmonic. So it's like adding two frequencies of different. Adding two different frequencies together and then seeing like the different the different like kind of time scales and stuff. So we'll see that coming up. And just to point out, capital M is the sum of the masses of the two objects. And then also eta is the reduced mass ratio. So that's M1 times M2 divided by the total square. So I'm going to show you what the application looks like. I also shared the sound, so you should be able to hear the sound signals through here and everything. So if you look, there's just, this is the default. It's funny, actually, Michael mentioned in his presentation that the lower limit for neutron stars is 1.4 solar masses. And that's what I have the application by default. So you could actually adjust these. and it will generate the plot fairly quickly. And then also there's a drop-down menu here that could change your device. So if you're using like a laptop, for example, in a classroom, like students have Chromebooks typically, the speakers probably start at like anywhere between like 90 and 120 hertz. So that's where the sound is going to start. But then on the computer I'm using now, I have like subwoofers. So it could start down at like 40 hertz, or I tested it with headphones and that kind of stuff. So that will alter the signal, and I'll show that coming up. But I'm going to play this, so you should be able to hear it. If your volume's loud, you might want to turn it a little bit down. I don't want to alert anyone. Were you able to hear that?
Mm-hmm.
Okay, cool. Yeah, so what we could do is we could alter things in here. So I could adjust this this dummy constant that I was talking about. So I put it from 0 all the way up to 1. And if I zoom in on this here, you'll see that it kind of alternates now. So instead of like every crest progressively getting bigger, now it's like it goes up and down and up and down. So it's like overall in the long time scale, it's like increasing and has the same behavior. But on the shorter time scale, it's like it's oscillating essentially. So now I'll play this, and this will sound a bit different. So you kind of hear like it sounds like 2 frequencies at the same time. And there's also a frequency versus time plot down here. So this shows you the initial frequency for this device is about 120 hertz, or it actually is 120 hertz. And then it goes all the way up to, it looks like a little bit over 1400, 1500, something like that for this plot. And then what I could also do is I could, if I lower the frequency on here, the initial frequency, it generates a lot more data points. So before this, the signal was only like a second or so long. And then now this is over 25 seconds. The problem is if I play this on Zoom, you're not going to be able to hear anything probably below, I don't know, it depends on what device you're on and what frequencies Zoom actually will, send through the call and that kind of stuff. But we probably won't hear anything up until like the very last couple seconds, but it will sound identical to what we saw before. So the first application that I showed before used like analytic solutions, as I showed on that slide. And we actually wanted to make another application. So that focuses on kind of like generating your own gravitational wave events. Like you could pick masses that have never actually been detected or anything like that. The second application is like a modified version of the first one, but it actually works like entirely different, even though at the surface it looks very similar. So what we did was we used real gravitational wave data for real events. So you will see over here, like all these are gravitational wave events. And these are just like a handful of them. There's like about 100 detections now. And now they're detecting more and more stuff all the time. So you will see that these are like mass, these are like different parameters. So this is like the mass in terms of solar masses. This is like chi effective. So there's basically 62 parameters altogether when they collect this data to describe these events. So the thing is, with all these events, there's lots of noise, like I mentioned before, and the signals are really weak. So there's a lot of uncertainty in the data. So when we get a gravitational wave signal, we're not always sure exactly what the masses are of the events. Like we'll say like maybe one was 28 solar masses, one was 30 solar masses, but then there's like margins of error on those. So maybe it's like plus or minus like 3 or 4 solar masses or something like that. So that's why we kind of have probability distributions for each of these events. So you'll see that like the mass, I guess this is the total mass in this case. It looks like the peak of it is about at like 8, if I had to estimate based on this plot. And what we could do is we could go in and we could look at the real gravitational wave data, and we could find the highest, like the maximum likelihood for each parameter, all 62 parameters. And then what we could do is we could feed it into a waveform generator. So I did that in Python. And so for each event, it varies depending on, the event and the masses and how much data there is and stuff. But the data comes in these files called HDF5 files. And you could think of it as like an Excel spreadsheet kind of thing, but holds way more data, has like multiple spreadsheets, has like subdirectories and other kind of things in there, like metadata and that kind of stuff. So on this big spreadsheet, for some of the events, it's like 62 parameters, and then there could be like 30,000 posterior samples. So one of those 62 columns is the log likelihood. So that is just basically the likelihood of how likely it is to happen. And then we take the log of it to just kind of scale the numbers down and make it like it's not going to change the order, the likeliness of it or anything. So I wrote a Python program that basically opens up these files, locates the correct directory, digs through that one column. So it searches through all 300,000 values, or, you know, give or take, because it changes depending on what event. So it looks through that whole column, picks out the highest likelihood value, and then saves that index. And what it does is it spits back the corresponding values for all 62 parameters. So then we know what the maximum likelihood like masses are and that kind of stuff. So we then feed that into a waveform generator, and you'll see that the plots we get end up looking very different. So these are actually more accurate than the other ones. For example, on this other application, there wasn't like a ring down period. So there's actually like behavior after they merge together. So this peak is where the black holes would merge together. And then there's actually still a like strain after that. And you'll see that this actually has the ring down period. So this is like where they merge together, and then it merges, it rings down, and then it gets to 0. And then it, you know, just remains at 0 after that. So right now we only have 3 events in here. Like I said, there's about 100 events. So there's this drop down menu, and you could just change it out. And these gravitational waves, basically the names have like the date in them. So this is like, the one we're looking at here is March 16th of 2020. And then this is, gives you like the time that it happened during the day. So you could also like sonify it, and I used like the same kind of code. As you can see, like these look very similar. And I could hit play waveform on here. And this is going to be a little bit harder to hear. The reason why is because this starts at 20 hertz for all these signals. And that was just a choice we decided to make. So my speakers, like I have like pretty good like bookshelf speakers over here, and I can't hear 20 hertz on it. A lot of people's ears can't even hear 20 hertz. So you won't hear it all the way until it's like probably over in this range. So I'm going to hit play, and you won't hear anything for a little bit. And then it's going to be a really, really quick sound. Did you hear that? No. So just at the end here, like probably just this part was audible. Everything before that is probably too low of a frequency to hear. So we plan on putting more gravitational wave events in here. We want to put all of them in here, but the thing is they're finding more and more stuff. So I guarantee by the time I put all like 90 or 100 detections that are currently in here, they're going to publish like probably like 100 more or something like that. And I have some acknowledgements here. So Dr. Favada, the chairperson of the physics department, was my advisor for this project. Dr. Ghosh, he helped me with a lot of the Python coding, and Michael mentioned him before. And then I have some other ones too. So, you know, Montclair State for providing my education in physics, mathematics, applied mathematics, I guess too, teacher education, and then some that involve the code and everything too.
Well, thank you very much, Kevin. That was really exciting. What a neat project. And I hope someday you get all the first 100 of them in there. And
yeah.
then we shall see what happens, right? I have a question. Do you plan to write a lesson plan for high school students? How best to proceed, to try this, then try that, and write conclusions and things?
So I have a couple additional slides in here, and it's funny you mentioned that. And then I talked to Dr. Favada, and we tried to pick and choose because we had a time restriction, everything like that. So one of the things in here, the second bullet point, is create assignments for high school teachers and students that could align with this application.
Cool.
Yeah,
Yeah.
so actually Dr. Favada and I were talking about doing outreach to high school teachers and trying to bring this material into the classroom, because a lot of times like the class I teach in the curriculum is like Physics 1, which is several hundred years old at this point. So we want to try to get some more modern physics topics in there that students are interested in, that kind of stuff. And we want to do like a kind of like outreach training kind of thing that brings in high school physics teachers to Montclair. And it would be like a professional development in some sense. So we would show them like applications like this. We would show them like the laser lab that we have and that kind of stuff. We have model interferometers and everything. And ideally, we would have a bunch of lesson plans and assignments that would go hand in hand with this, or project ideas and stuff like that.
Very good. Thank you. Any other questions?
I have a comment. What I would suggest is if you could also think about a middle school lesson plan, because once the kids get up into high school, their courses are somewhat tracked. And if you could pique their interest when they're more curious, when they're like 11, 12, I think that would be really nice and an opportunity for them to think bigger.
Absolutely. Actually, I went through the teacher education program a number of years ago through Montclair, and I did my like clinical 1 placement, which is like 1 semester of just assisting in the classroom. That was at a middle school. So I have like a fair understanding about like what they do in middle school and the curriculum and that kind of stuff. And I think this could really be adapted to middle school. I mean, it would just need different assignments and that kind of stuff. But I think they're capable of using this application as just manipulating some sliders and pressing some buttons and making some observations and recognizing the trends.
Great. What a good idea. Yeah. Any other questions? Well, thank you very much. We'd like to thank all of the speakers. This has been various and wonderful, and give us lots of things to think about. And we're proud of all of you. So thank you very much.